Okay, so we're starting a new chapter, our last chapter. And the general topics is topics in analytic geometry. Now we're going to do it in a different order than is shown in the textbook. We're going to start with circles and ellipses, then go to hyperbolas, and then back to parabolas. Because the one you're going to be most familiar with is a circle. So they're called conics because what you do is you have a three-dimensional cone shaped, like paper cups that are cones, and you have going in the positive direction here and the negative direction. This would be the origin, and it's a three-dimensional object. The cone is. But then what you do is you take a plane, which is like a flat piece of paper, and you cut into the conic. So you can just think of this as like a hologram or something, and you stick it in there, and the intersection of the flat surface with the cone creates this shape. And if you look down, if the plane here is perpendicular to the axis of the cone, which goes up through here, then you get a circle. And also the cone is a circular cone. So you can have, I guess you could have, well, I don't know, I think these are all circular cones. So if you go horizontally, you'll end up with a circle, the intersection of those two. Now the next one, which is the circle is a special case of, is an ellipse. So with an ellipse, instead of having your plane horizontal or perpendicular to the axis of the cone, it's at an angle, and so it gets stretched out. We think of another word that we would think of with an ellipse as an oval, but we'll find out that a circle is a special case of an ellipse in terms of how it's defined numerically. A parabola has the plane at the same angle as the angle of the cone, and so this plane only intersects this top cone. It never intersects the bottom cone. So that is a parabola. Because we think of parabolas as y equals x squared or some variation of that. And if you go back to chapter 2, first section, it's called a quadratic function. It's not, we don't call it a parabola, I don't think. No, we do call it a parabola. So let's see how that, I'm trying to remember if it says where you define a parabola, because that's kind of interesting. They talk about, oh, here we go. A graph of quadratic function is a special type of U-shaped curve called a parabola. Okay. Now hyperbola, what we have is we have the plane, the pink plane here, aligned vertically. So it's parallel to the axis of the cone. And if I move this closer to the axis, this point of intersection would happen more quickly. But a hyperbola has two parts. It has an upper part and a lower part. Or if the cone is horizontal this way, then it can have a left part and a right part. So those are what we would call basic cones: circle, ellipse, parabola, hyperbola. They're also what we call degenerate conics. They're kind of special cases. So if you have your plane aligned with the origin, or wherever this cone is originating from, where it has 0 dimensions here, that would be a point. But that's a very specific point. So the bottom of this cone and the top of the other cone. We don't really use these degenerate cones. It's just demonstrating you could create other shapes out of a cone and a plane. If you have the plane aligned with the angle of the cone but going through the origin, then you have a line. If it's not aligned with the origin, then you have a parabola. And if you have a plane that's parallel to the axis of axis of the cone, and it goes through the origin, then you have two intersecting lines. But that's just kind of a special case. Okay, so now we're going to talk specifically about circles and ellipses. We're going to talk about ellipses first, and then we'll tell you what the special case is for circles. So here's the definition, and it doesn't have anything to do with the drawing we had, but this is kind of the mathematical description. The only thing in the description as conics is just to show that they are related, but that's about it. After that, we're just going to treat them as two-dimensional curves, and they're not functions because we're going to see that it fails the vertical line test. So we call these relations or expressions. We wouldn't call them functions. We wouldn't say the ellipse is not a function. Okay, an ellipse is the set of all points x, y in a plane, the sum whose distance from two distinct fixed points called the foci is constant. See the figure. Okay. So here's the figure. So we have 2 points, and let's just pick some point in space, the initial point that's on the ellipse. So there's going to be a distance d1 to that point from this focus, and a distance d2 to this focus. And what we want to do is we want to have all the points that are in this two-dimensional space that have the same sum of the two distances. So if we were to draw, let's say this is an ellipse, well what's the restriction of the ellipse? Well, if I take another point here, let's say this point, and so I've got a new point, x1, y1, if you want to call it that. And this would be d1, and this would be d2. The sum of these two, d1 plus d2, for this point is going to be the same as the sum of the distances from these same two focus points to another point in an ellipse. Now, you can actually draw an ellipse on a chalkboard. What you do is you take a piece of string that's the sum of these two lengths, d1 plus d2. You would pin them, if there was a nice way to pin stuff to a chalkboard. You would anchor these points, and there'd be slack in it, and then you would pull on the string until it was tight. And so if I were to take the string and I were to pull it in this direction, the total length would still be the same because I'm not changing the length of the string, and I'm getting this sharp angle between the two. So anywhere on an ellipse, if you pick any point on an ellipse and you measure the distance from that point on the ellipse to these two focus points, d1 plus d2 is always a constant. Now a circle, the focus points are identical. So then what you get is you'd have a string that would go out from the center to the circle, and you'd have these two pieces of string right on top of each other. Now there's a couple of terminology here. So you could either have the long direction in the x direction or the long direction in the y direction. In this case, we have the long direction in the x direction. So if we look at this thing, the major axis is the longer of the two axes. I guess axis is the longer axis. The minor axis is the shorter axis. And the axis goes from all the way along here. Okay, so that's the axis, and that's the axis. It's not from the center. And ellipses are symmetric, and the center is the middle of the ellipse. So if I draw this major axis from one end to the other, and these endpoints are called vertices, or this is a vertex and this is another vertex. If I draw a line between those, and the same midpoint on this part of the ellipse, this is not called a vertex. Yeah, the question is that called a vertex as well? Well, it doesn't show it, so let's just assume it's not. This is just a point on the minor axis. And these lengths, so what we have is the length of the axis, even though this is the major axis, the length of the axis is from the center, as we'll see in a second. Anyway, that's the terminology. Now we haven't shown the focus points yet. Those are always along the major axis. So let me just write that down. Foci are always on the minor axis. So here's kind of a picture. Let me put this on one page so you can see it. This actually shows the focus points. And so I'm going to, let me just define some measured distances here. So the distance from the center to the vertex, that's A. The distance from the center to the focus points is called C. And then the distance from the center to this other point on the minor axis is called B. So that's how we designate it. So if this is B and this is C, then we have a right triangle in this case, and you can see that C squared, this distance here, which is one side of this triangle, plus B squared, which is this side of the triangle, equals this side of the triangle. And you can do the same thing on the other side. And it turns out that if we take the so it's trying to explain how we get this relationship. We get this relationship that A squared is equal to B squared plus C squared. And that kind of makes sense just from a magnitude standpoint, because these two are shorter. This is the longest one. A is the longest one. So let's see if we can figure out why that's the case. So they're showing that 2 times the square root of A squared plus B squared equals 2A. So what would happen is, if you can think about, there's this case, this general case at any point on the ellipse. You can also look at the specific case of where it's aligned. So you'd have the string would go here, and then it would go back like that. And if I take that distance, that's going to be, if I go all the way to here, and I add this little bit that comes back, that because of symmetry, that little bit that comes back is the same as this length. So this returning length can kind of go over there, and you can see that. So we have the entire length of the major axis, and the major axis is 2 times A, because A is this distance from the center to the vertex. So you take 2 times A is going to be equal to this distance plus this distance, because it's always the case that on an ellipse that the sum of the distances have to be the same. So that's where you get that from, and then you divide both sides by 2 and you square both sides and you get this relationship between the length of the minor axis, the length of the major axis, and the distance from the center to the vertex. Now this h comma k are the coordinates of the center. You don't have to have the ellipse centered at the origin. There are special cases, and we'll look at that. So that's kind of explaining how you get this relationship between the different lengths. So what is a circle? Well, a circle is where so let's say a circle is where both foci are coincident. That just means they're in the same spot. So you just move these as these foci come together as they approach this center of the ellipse, then the ellipse becomes more symmetric and becomes more like a circle. And when they actually meet to each other, then it just becomes a circle. So that's what a circle is. Okay. Now, the standard form of a circle, it looks something like this. And all of these pieces of information help you plot it. So h and k are the center of the circle. A is the length of the well, it's half the length of the major axis. Here, this is B is half the length of the minor axis. And then you could, if you wanted to plot the focus points, but you don't really need those to plot to make a decent plot of an ellipse, you could find the focus points by taking a squared minus b squared and taking the square root. Now, in the second case, this is the case of a major axis is horizontal. If you have the major axis vertical, what happens is A is now the denominator in this second term, because A is always larger than B. So whichever one's the largest, we call A. And that's because if C squared is equal to A squared minus B squared, then A's got to be bigger than B, or A squared is not going to be greater than B. So how do we plot ellipses that are in standard form? No, notice it's not a function. I don't have y equals something. If I tried to solve for y, I'd actually get something that involves the square root plus or minus the square root. So there'd actually, you have to have two functions to define an ellipse. But in this form, which we call, it's an explicit form of this relationship, an implicit form of this relationship. We don't solve for x or y. You'd plug in x and then you'd figure out what y is. Or you'd plug in y and figure what x is. So here's kind of a drawing. And what I do is, once the equation's in standard form, I draw the center, because I'll know h and k, and then I count to the right however many units it is, a units, to get this extent of the ellipse, and I go negative a direction and I mark that point. And what I really do is I make a square where the sides of the square are such so that it's tangent to those lines are tangent to the vertices of this thing. So that line's here, that line's there, this looks pretty good. I'm going to pull it down just a little bit. And once you have the square, you can kind of draw this ellipse inside the square. So I plot the center point, I count over a units from the center point. I draw a vertical line at that point. Plot the center, go over to the left, a units, draw a vertical line there. Then I go vertically, I go b units up, draw a horizontal line, b units down, draw a horizontal line. And then I know that the ellipse touches the midpoint of these lines that correspond to this rectangle. And then I can sketch in a curve such that it's smooth. I don't draw straight lines. I want it so that it comes to a vertical line here gradually, and it comes to a horizontal line here, a curve gradually. So this is the case of the horizontal axis being the major axis. So it's stretched horizontally, but you could also stretch it vertically. And in that case, the larger denominator is with the y term. And again, I would plot the center of the ellipse. Then I would count over horizontally, whatever the denominator of the x is, the square root of that I count over that far, and I would draw this box to help guide me drawing this ellipse. It's just easier to draw the box, kind of provides some structure to everything. So we'll do this quite a few times, so you'll see it. You won't have any problem. Okay, so I think we're going to do, before we finally take an equation and plot an ellipse, is we want to talk about eccentricity. And that's basically how much the ellipse is stretched in one direction or another. So the eccentricity for a circle is 0. And anything that's greater than 0, you have more eccentricity. Because a circle, the focus, the length to the focus is 0, because that focus is the middle. Okay. So the first thing we're going to do is we're going to plot ellipses that are already in standard form. Now from the standard form we can find the center, the vertices, the foci, and the eccentricity. And then once we have those, we'll sketch the graph. So we're going to do 3 of these problems, and they're all in standard form already. So one thing is, a circle usually have x squared plus y squared equals, say, 4. That's a circle of radius 2. In this case, we divided by the number such that the right-hand side is 1. So standard form of ellipses has a right side equal to 1. And so if we look at this equation, we see that h is equal to 0 and k is equal to 0, because we don't have x minus anything or y minus anything. So that means the center of the ellipse is the origin. Okay. Now this is the larger term. So we're going to call a squared is going to be 25, and b squared is equal to 16. So a is 5 and b is 4. Those are the lengths from the center to the vertices of the major axis and the minor axis. Now what I think we'll do is we'll plot it, and then we'll find the vertices. Just easier to do that, I think, visually. The foci, we can calculate this c. Remember, c squared is equal to a squared minus b squared, or c squared plus b squared equals a squared. So in our case, we have a squared is 25, b squared is 6, so you get 9. So c is equal to 3. Okay, so we can calculate the eccentricity here, because eccentricity is E is C divided by A. So we get 3 divided by 5, 3/5, 0.6. Okay, so let's get a piece of graph paper. Okay, so plot the center. So that's the center. The next thing you do is you go in the direction 5 units. So let's do that. 1, 2, 3, 4, 5. So that's that way, and you go the same the other way. 1, 2, 3, 4, 5. You start at the center, you go up 4 units. 1, 2, 3, 4. And go down 1, 2, 3, 4. Now let's draw a square or rectangle that encompasses these 4 values. I'll fix the alignment here in a second once I get something on the paper. That one looks pretty good. This one's a little off. This one's a little short. And I'm going to go ahead and sketch it in. So what you'd start off is this thing's vertical, and then it would kind of loops around like this, so that it comes in gradually to flat, then it's flat, then it gradually curves around here to there. You can kind of do it the other way as well. Okay. And let's plot one more point, which is the vertices. So you always go along the major axis. We go 1, 2, 3 units here, so that's a vertex. That's a foci. 1, 2, 3, that's a foci. Okay. So from this, so the vertices are this point. So it's going to be 1, 2, 3, 4, 5, 5, comma 0, and the other way, 1, 2, 3, 4, 5. So that's -5, -5, comma 0. The foci are 1, 2, 3, 3, comma 0, and -3, comma 0. And the center is 0, comma 0. That was from the H and K. So I think we've done everything. We kind of did it in different order. Find the center, vertices, foci, and eccentricity of the ellipse. Sketch the graph. So we found the center, sketched the graph, found the vertices, and we also could do the eccentricity. But you need the C value to figure out this. You don't need C to figure out the vertices. You do need to figure out the foci, focus point. Okay, let's look at another one. So again, this one's bigger. So a squared is equal to 64, or a is equal to 8. B squared, which is a smaller one, is equal to 28. So b is equal to the square root of 28. Now, because we're going to be plotting this, we're going to go ahead and put it in decimal form, because we're going to have some location on the axis. So let's just do the square root of 28 and see what it is. Should be a little more than 5. So this is 5.29. Let's go ahead and calculate C. So remember, C squared is equal to A squared minus B squared. So you have 64 minus 28. So 64 minus 28 is 36. So C is 6. That's why they chose 20, square root of 28. A lot of times the vertex is kind of a weird number, but they've chose the minor axis length to be a square root so that the foci were normal. Okay, so let's pull out our graph paper here. Again, because we don't have anything, we don't have quantity of x plus or minus something, the center is again the origin. So we can plot the center. And then we'll count over 8 units to the left and the right to find the vertices. 1, 2, 3, 4, 5, 6, 7, 8. Go the other way, -8. Then in the y direction, you have the square root of 28, which is 5.29. So we go 1, 2, 3, 4, 5, approximately there. 1, 2, 3, 4, 5. So that's the minor axis, and the focus points are plus or minus 6. So it goes there, and it goes there. So let's go ahead and draw in this box. So we're going to have a vertical line here. We're going to have a vertical line here. We'll have horizontal lines that go through that point, and horizontal lines that go through that point. And then we could sketch this thing in, so it's the same kind of deal. You come up here, you know, I have to draw a few of these to kind of get good at least doing a decent, but just don't draw straight lines between them. That would look terrible. I mean, it doesn't have to be perfect. Okay. So now that we've got that drawn, the vertices are these points. So that's 1, 2, 3, 4, 5, 6, 7, 8, 8, 0, and -8, 0. The foci are, so we go +6, so it's going to be 6, 0, and -6, 0. What else do we want to know here? The center, we already did that. That's 0, 0. And the eccentricity, E is equal to C over A. So we get 6 over 8, which is 0.75. So this is a little bit more stretched out than the previous one, which is point something. I don't remember exactly what it was. I'm going to insert one here that's different than I have. So let's say we have, we'll do two things different here. We're going to have x minus 2 squared divided by, let's say 9 plus y plus 3 squared divided by 25 equals 1. So you can see now I have a center that's not 0. So h is 2 and k is -3. A squared equals 25. That's the bigger one of the two. So a is 5. So this is going to be a squared, and this is going to be b squared. So we're going to have the major axis in the y direction, so it's going to be stretched in the y direction. Okay, so we have b squared is equal to 9. So b is equal to 3. And then we have c squared is equal to a squared minus b squared. So we get 25 minus 9, which is 16. So c is equal to 4. So now with the center and A, B, and C, we can sketch the ellipse. So now we're going to plot the center, which is not the origin. It's going to be, and I keep forgetting to put my scales on here. I guess it's default. If you don't see any scales, it's 1 unit. Okay, so what we'll do here is we will plot the center. So that's 2, -3. It's right there. And then we'll count 5 units in the y direction, because this A is associated with the y. So you go 1, 2, 3, 4, 5 here, and you go 1, 2, 3, 4, 5 there. Now, for the minor axis, which in this case is the x-axis, you go 3 units. So you go 1, 2, 3 units, and 1, 2, 3 units there. Now, the foci are always along the major axis, because if we counted 4 this way, we'd be outside the box. So we got to stay inside the box. So we go 1, 2, 3, 4, and 1, 2, 3, 4, like that. And then we can draw our box. So we'll have a horizontal line going here, vertical line going there, vertical line going there, horizontal line going there. So if we drew this ellipse in, again, we'd start off kind of real close to the surface, then we come up here, wait for a while till we start to turn. Do the same kind of thing here. Come down, loop around it a little bit, go through there horizontally, come up here, make sure we go through this vertically. And so that is our ellipse. So now, what can we say? Well, we can say the center is 2, negative 3. 1, 2, negative 3. That corresponded to 2, negative 3 from the equation standard form. The vertices are the ones along the major axis. So here's one vertice. So you start at the origin, 1, 2, 1, 2. So one of them is 2, 2, and the other one is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Negative 8. Sorry, 2, negative 8. The foci, those are the green points, they're still 2 all along that 2. The center's along 2. The vertices are along 2. The only thing that's not along 2 is these points on the minor axis. Okay, so I'm on this green point. So I go 1, 2, 1. So that's 2, 1. And I go 1, 2, 1, 2, 3, 4, 5, 6, 7. So that's 2, negative 7. And the eccentricity, E is equal to C over A. So that's 4 over 5, which is 0.8. That's even more stretched out. Okay, we're going to do one more. It's already in standard form. Now, one thing you don't see is a denominator here, so you always assume it's 1, which it is. So in this case, h is equal to negative 2, x minus h, so h has to be negative 2. K is equal to negative 4. A, this is the bigger one. Well, a squared is 1, so a is equal to also 1. Square root of 1 is 1. B squared equals 1/4, so b is equal to 1/2. And c squared is equal to a squared minus b squared. So we have 1 minus 1/4, which is 3/4. And if you take the square root, c is equal to the square root of 3/4, or the square root of 3 over 2. Now, this is going to be a small ellipse because these numbers are small, but we'll still do it. Just have to draw a small ellipse. Part of the reason we can't expand things too much is because the center is, away from the origin. Okay, so same procedure. Well, first let's label the axes. So center is -2, -4. So there's the center. The x-axis is the major axis. So we go 1 unit left, 1 unit right. So that's that part. We go up a half a unit right there, down half a unit, and we draw our rectangle. We could put the focus points in there in a second, but let's just draw the box first. And again, the focus points are along the major axis. So there we'd go square root of 3/2, which is 0.866, so it would be about right here. And you go the same distance, so that's where the focus points are. And then you could draw this in. It's going to be very small, but again, you go from the vertices around here like that. So the center, that's a single point. That's -2, -4. The vertices would be, so this is one of the vertices, the other one. So those are actually on the grid, so that's good. So one vertex would be, you go -1. So we go -1 and then 1, 2, 3, 4, -4. And the other one would be over here, which would be -3. So we'd have -3, -4. The focus points are here green. So you'd go over, so what would that be? So you have to do a little calculation here. You'd have -2 plus the square root of 3/2, which would be, let's just find a common denominator. So that would be -4 plus the square root of 3/2. And that would be this point. Now the y value is -4 for both of those, so we're still at the same y value as these other things. These all have the same y value. And this one would be, actually, yeah, let me, -4 plus the square root of 3/2. And then this other point would be -2 minus the square root of 3/2, which would be -4 minus the square root of 3/2, sorry. So they look very similar. It's -4 plus or minus the square root of 3, okay, over 2. So we get -4 minus the square root of 3 all over 2. And the eccentricity is c over a, so that c is the square root of 3/2 divided by a, which is 2, or is 1. So that's going to be the square root of 3/2, which is equal to 0.866. So that's even more stretched out. Now there are some equations that tell you, I think, what the vertices are. I think. Maybe not. Just trying to see if there's another way of doing this if you don't quite understand. No, they actually, you just have to kind of figure it out. You know, it depends upon, basically what you're doing here is you're taking the center coordinate, -2, and you're adding and subtracting the value of c. So if we call this h and this k, we could say that the focal points are going to be h plus c, comma, k, and this would be h minus c, comma k. So you could represent them as equation form. Okay, so that's the first thing. You just got to know how to plot them once they're in standard form. Well, what if they're not in standard form? So then you have to convert these to standard form. And it's a whole bunch of completing the square. So you may not have liked to do it before, and you're hoping you never see it again, but sorry, it's going to show up. Okay. We actually have to do it twice, once for each variable. So what we do is they typically have x squared, xy constant. What we do is we group the two terms that involve x together. So you get x squared minus 8x, and then we leave a little space, and then we have plus 5y squared minus 30y, leave a space, and then move this number to the right hand side. So this negative 39 becomes positive 39. Then what we do is let me just shift everything over a little bit here as far as I can so I have room. Okay, so we take this number 8, negative 8, and we divide by 2. You always divide it by 2, and you square it. So you get negative 8 over 2, which is negative 4. Square that, you get 16. So we add 16 here. Here we take negative, well, yeah. So that's what you do when you just have x squared here. In the second case, we have to go one more step. So let me just write that in. So if you have something y squared, you need to factor that out of both terms that involve y. So you get 5 times y squared minus 6y. So negative 30 divided by 5 is negative 6. And before we do that, let's go ahead and add 16 over here, because we added 16 to the left hand side, so we need to balance that out. Now here you still take negative 6, divide by 2, square it. So that's negative 3 squared, which is 9, so we add 9. But what we're really doing here is we're adding 45, because we have to multiply this by 5. We're adding the 9 inside the parentheses, so we have to multiply that 9 that we added in parentheses by 5 to represent this factoring. So we add 45 here, so we're going to add 45 over here as well. So I add 16 here, add 16 there, add 45 here, add 45 there. Then you can take this and you can make it into a complete square. So it's going to be x, and the number you use is this intermediate one. So negative 8 divided by 2 is negative 4. So it's x minus 4 squared. And then you have the next part, which is 5 times x minus 3 squared. I didn't show the intermediate step here, but if you take negative 6 divided by 2, you get negative 3 squared. So that's the number that's for the complete square. And then you add all the numbers up on the right-hand side. So you get 39 plus 16 plus 45 is 100. Oh, how about that? 100. Okay, so we're almost there. The only thing we have to do is divide by 100, because you have to have 1 on the right-hand side for standard form. So you get x minus 4 squared divided by 100 plus 5 times y minus 3 squared over 100 equals 1. And what we need to do is get this 5 in the denominator. So what you would do on the second one is you would take the 5 that's in the numerator and put it in the denominator of the denominator. Okay. So you'd have y minus 3 squared over 100 divided by 5 Now, I can rewrite, well, I'll just leave that as 100. Okay, don't need to rewrite that. So then you'd have, associated with the y, you'd have 100 divided by 5, which would be 20. Okay, so that's standard form. So now once you have it in standard form, you can find all the other stuff out. So the center is going to be at 4, 3. Because 100 is larger than 20, major axis x direction A would be equal to the square root of 100, which would be 10, and B would be equal to the square root of 20, which you could reduce that down to 2 times the square root of 5 if you wanted to, but probably don't need to, because we need that as a decimal anyway, so you can take the square root of 20 pretty easy in your calculator. So you take the square root of 20, which is 4.47. And c squared is equal to a squared minus b squared. So that's 80. So c is equal to the square root of 80, which again we can do that. So the square root of 80 is 8.94. Does that make sense? Yeah. Because if you think about it, this is 820 is 4 times 20 is 80. So the square root of, because you're taking the square root of 4 would be 2. So this one's double that one. So we can calculate the eccentricity here. It's going to be equal to c over a, or 8.94 over 10. So it's pretty round. Or is that, no, actually it's more stretched than I thought it was. Okay, it's 0.894. Okay, so here we go. Now we're going to plot this thing. And then we'll get the vertices and everything off of the graph once we get that. Okay, so here we go. Plot 4, 1, 2, 3, 4, comma 3. Let's make this 10. Let's make this 10. Negative 10. Negative 10. Okay. So A is 10. Ooh. Yeah, I'm going to run out of space, aren't I? Well, let's move the axis over here. Oh, I can't do that. It's not going to work. Yeah, I'm actually going to have to change the scale here because I'm going to go off my graph. So this is, let's say that's 20, this is 20, this is negative 20, it's negative 20. So now I'm going to rewrite this. So what are we? We're 4, 3. So just erase that. So this is 2, 4, 6. So 1, 2, 2, 3. That puts me right here. Then we go 10 units. So this is 2, 4, 6, 8, 10. That's there. 2, 4, 6, 8, 10. Puts me there. Then from the center I go up 4.47. So 2, 4, just a little bit more than that. I'm not going to be any more accurate than that. 1, 2, 4, a little bit more. Okay, so then we can draw this box. So we got a horizontal line here. Going to draw another horizontal line. Vertical line through here. One through there. Now our focal points are going to be 2, 4, 6, 8, 9 would be right in the middle there, so it's probably going to be right there. Well, those are way out there, aren't they? And finally, if I draw my ellipse, it looks something like this. We have to come all the way out to there, comes down there, goes to there, like that. So the center is at 4, 3. The vertices, well, let's think about what we're doing here. We're starting at x equals 4, and we're adding 10. And we have the same y location. So this is all along the same line. So the vertices, the center, all have the same y thing. And then you'd have 4 minus 10, comma 3. That's what I did counting. So you get 14, comma 3, and negative 6, comma 3. So you can see that. 2, 4, 6, 8, 10, 12, 14, 3, and then 2, 4, 6, so that's negative 6, comma 3. So that works out. Now you do the same thing here, but instead of adding 10, you add 8.96. And you subtract 8.96. So this one will be 12.96, comma 3. This one I got to use my calculator for. 4 minus 8.96 is negative 4.96. comma 3. So that's the coordinates of foci, and I already did the eccentricity. Okay, so we've got 2 more problems. I have to convert them, put them in standard form. So we've got the x's here, so we actually have to move things a little bit. So you get 16x squared minus 32x. And then we've got the y terms, 25y squared plus 50y. We'll go ahead and move the 16 to the other side, so we get negative 16. Now we're going to factor out the constants that are in front of x squared and y squared. So if we do that, we'll get 16 times the quantity x squared minus 2x. We'll leave a space, plus 25 times y squared plus 2y equals negative 16. Okay, now here we take negative 2 divided by 2, square it, so that's negative 1 squared, which is 1, so we're going to add 1. Now we're adding 1 inside the parentheses, but we're actually adding 16. 16 times 1, which is 16. Now over here the same thing happens, except you got plus 2. So you take plus 2 divided by 2 squared, which is 1 squared, which is 1. So again, we add 1. But we're really adding 25, because we have 25 times 1. So that's 25. So on the right-hand side, we're going to add 16, and we're going to add 25. So this one is adding 16, this one is adding 25. We have to add it both to the right-hand side. So we have 16, and then you can make this into a complete square, which is going to be x minus 1 squared. Use that number. Then we have plus 25 times y plus 1 squared. Use that number. And that is equal to 16 minus 16, that's 0, plus 25, so it's 25. And then we divide both sides by 25, so each term gets divided by 25. 25 divided by 25 on the right hand side. Again, we want to take the reciprocal of the fraction we have here and then put that in the denominator. So it's 25 over 16. Here we'll get 25 over 25, which is 1. And that's equal to 1. So we get x minus 1 squared over 25 over 16 plus y plus 1 squared over 1 equals 1. Now 25/16 is larger than 1, so as before, the x-axis is the major axis because it's the longer one. And so A, which is the length of the major axis, is going to be equal to 5/4 because you take the square root of 25, you get 5. The square root of 16, you get 4. The square root of 1 is 1. So B squared is 1. So B is 1. And then you have that C squared is equal to A squared minus B squared. So you get 25/16 minus 1, which is 16/16. So that's 9/16. And then if you take the square root, you'll get 3/4. So C is where the location of the foci, or at least gives you an idea of what's going on there. Okay, so we're going to add, we're going to put a graph in there, and I'm going to change the scale to make this thing a little bit bigger. Otherwise, it's going to be hard to plot. So I think what we'll do is we'll make four tick marks to be 1. So this is going to be 1, 2, go the other direction, -4, -8. So it's -1, -2. We do the same thing in the y direction. We have 1, 2, and then -1, -2. There. And another thing we have is that the center is located at 1, -1, because here to get this to go to 0, you have to have x equals 1. And to have this go to 0, you have to have y equals -1. So that's where the center is. So let's plot the center. It's 1, -1. Now, the x-axis is the major axis, so we're going to go 5/4 to the right. 1, 2, 3, 4, 5. That's each one of those tick marks is a fourth. 1, 2, 3, 4, 5. There you go. The vertices, the foci are 3/4. So we go 1, 2, 3. There's foci. 1, 2, 3. Like that. The minor axis is 1 unit. So here we're at -1. So if you go 1/4, 1/2 of 3/4, that's +1 from the center. 1, 2, 3, 4. Minus 1 from the center. So now you can draw your box. So you've got this horizontal line here. You've got a vertical line here. You've got a horizontal line here. You got a vertical line here. So trying to get this thing to. Oh, it's because I got an eraser. I don't want an eraser. I need a little pointy thing. Okay, so just shift that over and get these aligned a little bit better. Okay, it looks pretty good. So if I now draw the ellipse, it's going to start out here. Vertical slope, and it's going to curve around. So you got to kind of go out in the corners a little bit. You can't just draw a straight line. If you go, that's easy, but it's not very realistic. And remember, the whole concept of an ellipse is that the distance from one focal point to the point on the ellipse plus the distance from there back to the other focal point is constant. So if I draw, a couple points here, the sum of these distances is going to be constant. That's the whole geometric principle of an ellipse. Okay, final problem. So we got 3x squared plus 18x. Put those together. Take the y's, just put them together. Move the constant to the other side. So as we change it to the other side, it changes sign, so it becomes positive 8. Here we don't have to factor out anything, but for the x part, we do have to factor out a 3. So factoring out 3 out of 18, you take 18 divided by 3 is 6. Leave some space. Here we don't have to factor anything out because we just have y squared, so leave some space, set that equal to 8. Okay, here we take 6 divided by 2 squared, which is 3, squared, which is 9. So we add 9, but we're really adding 27. 3 times 9. 27. So adding 27 here, so we have to add 27 to the other side. We always add numbers in these complete squares because we always square half of the middle term. And so anything squared is going to be positive. Okay, now here we have negative 2 divided by 2 squared, which is negative 1 squared, which is 1. So we add 1 here, and we don't have any multiplier out, so we're just adding 1. So we do that. Now we can rewrite the term in the parentheses as a complete square, so we get 3 times x plus 3 squared plus y minus 1 squared is equal to, and what we have here, 8 plus 27 is 35, plus 1 is 36. Again, standard form is this whole thing is equal to 1. So we're going to divide both sides by 36. So the right-hand side becomes 1. We take this one's okay, everything's fine. Here, we're going to have 36 divided by 3. This 3 in the numerator becomes the denominator fraction down here. And 36 divided by 3 is 12. So we get x plus 3 squared over 12 plus y minus 1 squared over 36 equals 1. So what can we say? Well, we can say the center is the point negative 3, 1 from the terms that are in the parentheses here. Now, the y-axis in this case, so since 36 is greater than 12, the y-axis is the major axis. So a now is this term. A is equal to 6, square root of 36. B is equal to the square root of 12. And therefore c squared is equal to a squared minus b squared. So that's 36 minus 12, which is 24, or C is equal to the square root of 24. So let's go ahead and get the decimal numbers so we can plot these. So 12 square root is 3.46, and the square root of 24 is 4.90. Rounding it off, 4.90. Okay, so now we can do our plot. Because we have a pretty decent major axis, we're just going to plot it with the normal scale. So we'll go from 0 to 10, 0 to negative 10, 0 to 10, 0 to negative 10. And so let's plot the center. So the center is at negative 3, 1, 2, 3, positive 1, right there. Now in this case, the major axis is the y direction. So we go from the center and count up 6. 1, 2, 3, 4, 5, 6. Go down 6. 1, 2, 3, 4, 5, 6. Now the foci are 4.9 up. So we go 1, 2, 3, 4.9, and we go down 1, 2, 3, 4.9. So those are focal points. And then we go the x direction, which is the minor axis. So we go 3.46. So 1, 2, 3, 4.46 is close to a half. So 1, 2, 3 and a half. And now we can draw our rectangle. So they go through the vertices, not through the focal points. I'll readjust these here once I get them in there, if I need to get them through these points. So this should be going right through there. This one should be going right through the center of the blue dot. This one's going right through the center of the red dot. This one's a little off center. Oops. Okay, so that's our box that's going to help us draw this. So we start over here. Let's start up here. So you can start at this along the major axis, and you're going to draw out towards this corner and then loop around. Probably went a little bit too far. Okay, so there you go. That's what it kind of looks like. Now, before we finish, one last thing is let's show you how you find the vertices. And we can get it from this drawing. So I'm just going to draw them on here. So you got 1, 2, 3, comma, and from the axis you go 1, 2, 3, 4, 5, 6, 7. So that's 3, 7 is this point right here. Down here, again, you go over 1, 2, 3 in the x direction, and you go down from the axis 1, 2, 3, 4, 5. That's negative 5. Over here, the y coordinate is 1, positive 1, and we go 1, 2, 3, 3.46. So we go 0.46 past the axis. So it's 0.46 comma 1. And then over here, it's comma 1 as well. So that's negative 3, negative 4, negative 5, negative 6, negative 6.46. Is that right? Because the total should equal twice the, if you double this, 7.92. If you add these two together, you should get 7.92. Is that right? Doesn't seem quite right. 1, 2, 3.46. Actually, it's not 6.92. So if you add if you take this 0.46 and you add the magnitude 6.46, you'll get twice this number. So that makes sense. And then the vertices here, the foci. So again, it's along this line. So it's going to be, then it should have been -3. I don't know why I put 3 in there. -3. So this is -3, comma. And so we started here at the center and we went up 4.9. So that'd be 1, 2, 3, 4, 5 plus 0.9. It's going to be 5.9. And then if you go the other direction, you're going to 1, 2, 3. Well, a positive 1, 0. 1, 2, 3, 4, 3. 1, 2, 3. -3.9. So this one is going to be -3, -3.9. So you can, instead of memorizing a formula, you can just figure out where you start and then do some counting to then add on to get the actual final values. I'd rather you understand it that way than just some formulas that you plug numbers into. You don't really understand what the heck's going on. Okay, so now you should be ready to do some of the homework.